So this is part 2 of this video. If you have not watched part 1, please go watch part 1. So last time I stopped on getting R equivalent and I found that it was 66.7 ohms. So now all I have to do is get my R total, and my R total is just R1 plus R2 plus R equivalent. So this is very, very straightforward. My R total is going to be 100 plus 100 plus 66.7. And I'm going to round up as I calculate my answer to 3 significant figures. So I end up with 267 ohms. All right. This was actually very easy. When you think about it, once you analyze what's in series, what's in parallel, get yourself an expression, it all becomes fairly simple. Okay? So next, I want to do a big circuit, and while we're gonna do the circuit together, please do take notes. By the way, on all of this, this is like your regular lecture. I want to introduce a few terms and a few definitions that are a little more grown up than what you have done before. We're still going to be talking about all the same things, but hopefully by the time we finish with the next circuit, you'll walk away with a better understanding of what it is to be in series and what it is to be in parallel. So let's take a look at our example circuit number 2. And this one has 9 resistors. And boy, does this one look complicated. Look at this. This looks very complicated. But I would start exactly the same way I have started before. I will start with identifying what is in series and what is in parallel. So let's go ahead and figure this out. Always start with series, guys. The series is always easiest to figure out. All right. So R1 and R2 definitely look like they are in series. So these two. This is R1 plus R2. So are R5 and R6 over here. These are in series as well. Now most people, when they look at this circuit, would say, well, R8 and R9 are in series. But it's actually not just R8 and R9. R7 is also in series with R8 and R9. So let's circle them as well. These three. Type this up. Okay. So in series, we've got R1 and R2, R5 and R6, and then R7, R8, and R9. To a lot of people, it is not obvious that R7 is in series with R8 and R9. And we need to figure out how can we make this obvious. And I'll tell you why this is not obvious. It's not obvious because we don't really have a very good definition on what it is to be in series. So far, we've been saying, oh, they're like beads on a string and things like that, like TV series episodes, one after the other. But that's not really a good definition, okay? So this is what we're working towards. Another interesting definition that is almost correct, and good job on that one, comes from David in my 8th period. And he said, well, they have the same current flowing through them. That is almost true. So let's go ahead and label all the currents. I'm just going to go ahead and do that. So first, I'm going to start with R total. So I have R total coming out of my battery. going through R1, going through R2, up until this point. This is where R total splits. Some of it goes into R4. Some of it will go to the right and eventually split into two more branches. Now over here on the bottom is a point where everything merges. And I once again get my R total back. And once everything merges, my R total also goes through my R3. Well, there is a little problem with this definition because the same current goes through R1, R2, and R3. And while R1 and R2 are definitely in series, R3 is not in series with either of them. So let's look some more at my currents and try and figure out why this is. So my second current is my R1. I'm gonna outline this branch in yellow. This is my I1. So once you get to this point over here, this big point, my current splits up. And over here on the bottom, this big point, my current merges together. The points where your current splits up and merges together are very important. They're actually called nodes, and we will need those points for a variety of definitions. So at this point, the current splits up into I1, and we can call this one I2. Once my I2 reaches this point over here, it splits up in two more branches. So let's outline this. So I'll have I3 going over here, and I'll have another color, let's call this I4, going over here. And once again, eventually they will all merge together. And over here, they're going to merge together. So this is my I4, and this is my I3. So there is something to be said about David's definition. Both R1 and R6 and R7 and R8 and R9 really do share same currents, right? I have turquoise current I3 going through R5 and R6, and I have the orange current I4 going through R7, R8, and R9. But once again, it still doesn't solve the problem of R3, right, which has the same current I total going through it, but it's not in series. So there is a very simple definition that we can use for being in series. If you look at all of the parts that are in series, you will notice that what they don't have is nodes in between them. Now, let's formally write down the definition of a node and then write down some other definitions as well. So, a node is a point in a circuit where the current splits up or merges. That's it. And now, knowing what node is, we can finally do a definition of series that makes sense. So, circuit elements are in series if there are no nodes between them. That's it. Very, very, very simple. Now, this is why, even though the same current is flowing through R3, it's not in series with R1 and R2. The reason for that is these two nodes in between them. As long as there is a node in between, they're not in series anymore. And that is really all there is for the nodes, right? And for the series. At this point, we have determined what is in series and what is not in series in this circuit. Well, the next question would be, okay, what's in parallel? So let's consider the whole circuit. Well, to most people, it would be quite obvious that R4 is parallel to R5 and R6. But it is also true that R4 is parallel to R7, R8, and R9. And just as R4 is parallel to R5 plus R6. So the question is how we can see this. It would have been a little more obvious if this resistor was behind this corner, right? But all those corners, they really don't matter. It doesn't matter how you bend your wire. It's still going to act as a wire, right? So far we've been basing our assumption that things are parallel just on how they look. Oh, these two lines are parallel, therefore resistors are parallel. Well, that's not really how it truly works. So next, I'm going to mess with your mind a little bit. I'm going to show you a picture of a circuit, and I claim that that circuit is exactly the same as the circuit I have over here. Okay, so take a look at this circuit, right? It looks completely different. One thing that I have in here that I haven't had before is I have this thing coming out at 45-degree angle that I did not have over here. So what's going on? Well, if you were to trace the currents, and that's what I'm going to do right now, you will see why this really is one and the same. So first, this is my R total, right? It goes through first two resistors, gets to this point, and then splits up. Over here it merges back. I'm going to put it back into my... Okay, once it splits up, let me see, I had I1 being yellow. I1 goes into R4. There it is. This is my I1. Now, I don't seem to have I2, but I do have I3 and I4, right? I3 goes through R4, R5, and R6. So I'm going to grab this turquoise thing, and I'm going to make an I3. And I4 was yellow, right? So orange. So let's get that. So, do I have I2 somewhere? Yeah, I have it over here, but honestly, I can easily delete this part as well. I can just twist them around and have them terminate into this node.